Yes, welcome everyone. I'm very happy to introduce our speaker for this week, which is Yihang Zhu. He's assistant professor at NUS Business School. He's been in Montreal before, as far as I'm aware.
Toronto.
Toronto,
Toronto.
sorry.
Yeah, it's okay.
We were just talking about it. Yeah, his research interests are widely speaking in optimization, but apparently he's also very much interested in robust optimization. He published already works in top journals like Operational Research, and also received several Best Paper Awards, including the Pearce Scholar Best Paper Award. I'm very happy that you're accepted our invitation, and please, Jan.
Thanks everyone for coming. Thank you, Giannis and Reza, for the invitation. As Giannis said, I'm Ian. I'm an assistant professor at the NUS Business School. And today I'll be presenting work that I started near the end of my PhD. So this is with my former PhD advisors, Merve Baudour, who has, I believe, presented in this webinar before, and Tim Chen. Before I start, let me just try to hide this. This. Let me just try to hide this somewhere. Okay. So let me start by giving just a quick one-slide summary of what this talk is about. All right. So in this talk, we're going to be focusing on a family of adaptive, robust binary optimization problems, or two-stage robust optimization problem. Okay, so for those who work in robust optimization, whenever you hear kind of two-stage or multi-stage robust with discrete variables, right, you should immediately feel that this is a difficult problem to solve. Okay, and if you're not in this area, right, you'll see very soon that this is a hard problem to solve. So the main kind of contribution of our paper and of this talk is that we're going to take these difficult to solve problems, these two-stage robust problems, and we're going to reformulate them as what we call constrained network flow problems. Okay, and we'll show that these network flow problems are versatile to use and they're easy, right? So I have easy in quotations because I'll define exactly what that means. Just to be a little bit more formal, right? What we're going to do is take these two-stage robust problems, and we're going to write them as a single mixed integer program. Okay, so our mixed integer program is going to look something like this, right? Where I'm minimizing a single linear objective where my W is subject to some constraints. And the punchline of our paper, right, is that this capital W, right, the feasible region that defines this mixed integer program is going to correspond to flows across one or several networks. Okay, so this is kind of the high level overview of this talk, right? And we're going to talk about how we get this reformulation and how we actually build these networks. Okay, and feel free to interrupt at any time if you have questions. Okay, so let's jump right into it, right? Formally, we're going to be studying these two-stage robust binary optimization problems with objective uncertainty. Okay, so in the first stage, I'm going to be picking a decision, X in capital X, and this is going to be binary. Once I make this decision, some uncertainty is going to be revealed to me, and I'm going to assume that it's revealed to me in an adversarial way, right? So the uncertainty set is convex. And then after this uncertainty is revealed to me, then I'm allowed to make another binary recourse decision. And note that here, the feasible region, right, only depends on X. Sorry, Giannis, can I quickly check with you? Can you see my mouse?
Yes, yes, we can see.
Okay, perfect. Okay, so note here that the feasible region doesn't depend on the uncertainty, right? So the uncertainty is only limited to the objective function. So this is really going to be a methodological talk, right? But let me just give a motivating example to start with. Okay, so the motivating example is a very classic facility location problem where we can think about two stages of decision making, right? In the first stage, I decide where to put my facilities. Once I put my facilities, transportation costs become revealed to me, And then I decide how do I service nodes from these facilities. Okay, so as a quick example, right, suppose these blue triangles are places where I can put my facilities. So in the first stage, suppose I put two facilities, right? And once I put them, the uncertainty, meaning the transportation costs are revealed to me. And then based on what my the transportation costs that I observe, I can decide how I want to service these red nodes, right? So for certain transportation costs, I might want to service it this way or this way. Okay, and more broadly, we can think about these problems as arising in any context in which you first want to reserve or acquire some resources before deciding how to use them later. Okay, so other examples are in networks, right? Suppose you want to first reserve or buy certain arcs, then decide how do I use those arcs. In scheduling problems, you can think about reserving a specific time slot and then later on deciding how to use that time slot. Okay, and more generally, I'm going to define this term selective adaptability, which is also in the title of this talk and in our paper. Right? So selective adaptability corresponds to constraints that look like this. Okay, so this just means that each element of y depends on an element of x, right? So as an example, if xi corresponds to whether or not I put a facility here, right? I can only adapt, meaning I only have a choice on y, right? If that y corresponds to arcs coming out of this facility. Right, so if my y's are these arcs and I don't put a facility here, right, then I can't actually send anything out of this node. Okay, so this is what we're going to call selective adaptability, and this is going to show up in a few slides. Okay, so how do we go about solving this problem, right? This is a challenging min-max-min problem, binary, convex, binary. Right, and really you'll see in the next slide that the trouble is really this inner optimization problem. So there's a variety of exact iterative methods, right? The most classic was a nested constraint and column generation approach, in which I sample scenarios and build a bigger and bigger master problem. There's tailored branch and price algorithms, most notably from Aisha Arslan and her co-author Boris Etienne. And I believe Aisha also presented in the webinar. And finally, there's branch and bound methods, and Giannis and his co-authors also developed these. So there's, aside from exact methods, there's also approximation methods, the most popular of which are methods that you can write as mixed integer programs. Right, so k-adaptability is, I think, one of the most popular. And so the idea behind k-adaptability is instead of allowing myself to choose any optimal recourse decision for any realization of uncertainty, right? I limit myself to k number of recourse decisions. And then by doing this, you can actually replace this thing as a large mixed integer program. Okay, so with this in mind, what we're going to do is we're also going to rewrite this, right, as a single mixed integer program. And again, the kind of key takeaway is that this capital W is going to depend on flows across the network. Okay, so with this mixed integer programming formulation, one benefit is that you can implement this and then apply this in standard solvers, right? You just have to code up this mixed integer program. I'll talk about how they're really versatile for approximations, mainly because you can design kind of the size of these networks. Okay, and then at the very end of the talk in numerical experiments, I'll show that these models can generate very high quality solutions in bounds. Okay. Again, if you have any questions, always feel free to interrupt. Okay, so what is the main reformulation idea, right? The main reformulation idea is to first look at this inner minimization problem, right? Which is kind of the main complexity of this min-max-min problem, right? Because it's a binary feasible region, you can't really apply certain reformulation or duality techniques that are relevant for convex programs. Okay, so the most obvious thing we can try is to see if we can get a convex reformulation, right, or approximation. Okay, so we're going to do exactly that. And we're going to do this by first writing our constraints, this set here, right? The feasible region that depends on X. We're going to write this is just by definition, right? As an intersection of two sets, okay? A set of constraints that don't depend on X, right? So just very generally AY greater than B, where Y is binary, right? So these are constraints that don't depend on X. Okay, and then constraints that do depend on X. And for the constraints that do depend on X, we're going to assume that this satisfies selective adaptability, right? Which is this idea of, I first acquire some resources and decide how to use them, right? So again, this definition just means, at least in this talk, right, we have a slightly more general definition in the paper, but you can think about it as just individual elements of Y are either lower bounded or upper bounded by individual elements of X. All right, so why is this useful? Right? So if I look at this inner minimization problem, right, which is a discrete program, right, the binary program, which was giving us a hard time, I can do a series of reformulations, right? So this is equivalent to this. Okay, so this is pretty straightforward, right? Optimizing in a discrete feasible region is the same as optimizing the convex hull of this feasible region. This is equivalent to this, right? And this is by definition again, because all I did was just define, right, as the intersection between constraints that don't depend on X and those that do. And really where selective adaptability comes in, right, is in this final reformulation, okay, where we can decouple capital Y from S of X. Okay. So we can decouple capital Y from S of X, right? And so really we can only focus on trying to get the convex hull of a set, a feasible region that doesn't depend on X. And then lastly, I just want to say that this assumption on S of X, right, actually comes without lots of generality. What do I mean by this? I just mean if you were to give me any two-stage binary, robust binary optimization problem, right, I can always reformulate it in a way where the linking constraints between Y and X looks something like this. Right, so I'm not going to do that here, but you can check out our paper, right? You can do this by basically adding a few auxiliary variables. And I do want to point out that a lot of this is inspired by Arslan and Detienne's paper, where they look at formulations like this and this, right? But instead, they pivot into looking at branch and price and cutout. Okay, so just a recap of what we've talked about and where we're going, right? So this is our original problem. It's a min-max-min problem. Again, discrete variables in the first stage, discrete variables in the second stage. This assumption of selective adaptability gave us this nice structure, right? Where we can now say this is a min binary decision, right? The max is over a convex feasible region. And then this min, if we had this convex hull, right, would also be over a convex set. Okay, so if I'm maximizing over a convex set, minimizing over a convex set, and this is a linear function, I can apply standard min-max-min technique, right? Where I can just min-max-min theorem, minimax theorem, sorry, where I can just swap the min and the max, right? So if I swap them, I get this. Okay, and note that this is just a static robust optimization problem, right? In the first stage, I make, not even in the first stage, I first make some decisions, discrete decisions X, continuous decisions Y, in a way that protects me against kind of adversarial realizations of Xi. Okay, so all of this is to say that the kind of main complicating factor or the main thing we have to handle is just to get the convex hull characterization of the capital Y. Okay, so this is basically where we're going to temporarily solve robust optimization, and we're going to focus on reformulating or approximating this kind of convex hull of a set, right, using decision diagrams and network flow models. Okay, so let me just quickly pause here if there's any question. So if not, right, we're going to talk about decision diagrams.
Yeah, maybe I will just ask
Yeah.
one question.
Yeah.
So I probably missed that, but why do you have this equivalence between the top selective adaptability and the static one? Because
You
of the
mean how do I
convexity
go
and the
from here to here?
compactness, right?
Yeah. So
Yeah.
if I have a
Okay.
this is the minimax, right? Yeah.
Yeah.
So if I max
Okay.
a linear, yeah. Okay, cool.
Yeah.
Thanks for the question. Yeah. Okay, good. Because in the next couple of slides, I'm really going to be focusing on how we get here, right? How we get the convex hull of capital Y. Okay, cool. Okay, so let me pivot slightly. Let me digress slightly. So what is a decision diagram? Right, so decision diagrams are graphical structures, right, that can encode a discrete feasible region. Okay, so here I'm citing a book on the use of decision diagrams to solve various deterministic combinatorial optimization problems. Right, so this is written by several co-authors who were all affiliated with CMU at some point. And the kind of key thing to understand is that in these decision diagrams, each path corresponds to a feasible solution. Okay, so the easiest way to see this is just through an example. Okay, so suppose this capital Y, right, looks like this. Okay, so it's defined by a single knapsack constraint, y1 plus y2 plus 2y3 plus 2y4 plus 3y5, less than or equal to 4. Okay, and so this, I'm just going to tell you, right, is a decision diagram for this feasible region. Okay, so how do I look at this decision diagram, right? I have a root node here. I have a single root node. I have a single terminal node. Okay, and I have 5 layers, right? And each layer corresponds to one of the Y decisions, right? So in this first layer here, this corresponds to decisions on Y1. And how I go about reading this is basically the dashed lines. You can think about as an assignment of value 0 to that variable, and the solid line as the variable, as the variable taking a value of 1. Okay, so just as an example, right, if I just go on the left side here, right, all dashed lines, because this is all dashed lines, this corresponds to solution 0, 0, 0, 0, 0, right, which is obviously feasible to this knapsack constraint. If I look at the rightmost path, right, I have, solid, 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 right? And note that when I do solid, 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 the only arcs that are left are these dashed lines, right? And the reason is because the first 3 solid arcs, right, correspond to, y1 taking value of 1, y2 taking value, y2 taking value of 1, y3 taking value of 1, and these add up to the capacity, right? So there's really nothing else I can do other than take these dashed arcs. And what is the reason why I'm talking about decision diagrams, right? It's because if I had such a diagram, right, remember that the main complicating factor in solving the 2-stage robust problem was getting this convex hull, right? So this convex hull you can actually get by the flows on this network. Okay, so let me just be a little bit more precise about what I mean by this, right? What I mean is if I had this decision diagram, then I can define a set of variables z, right, which correspond to the flow on the arcs of this diagram. Okay, and then all I have to do is, for the z, I define your standard network flow constraints. Okay, and then as well as relating the values of z to the values of y. Very specifically, the value of y is going to be equal to the amount of flow on the solid arcs of each layer. Okay, so let me just pause here just in case there are questions. Okay, so if not, right, how do we generate these decision diagrams, right? You can generate them using a recursive formulation of a deterministic optimization problem. Okay, so again, let's look at an example, the same example from before. And this is very closely related to dynamic programming, right? So for those who are familiar, right? So I can think about nodes related to, the state, right? So for this particular knapsack constraint, I can think about a state of 0 at the very beginning, right? For y1, if I choose not to add anything to it, right, the state stays at 0. If y1 goes on the solid arc, the state goes up to 1. Okay, for y2, again, if I go on the dashed line, this is the same thing as saying y2 is 0, right? So the state stays at 0. Okay. If y2 is positive, if y2 goes on the solid arc, right, that's the same as y2 taking value 1, so the state is 1, and so on. Okay, and while I'm building this diagram, right, at any point, if I see states that are similar or exactly the same in this case, right, I can merge them. Okay, and then I can keep building this diagram this way. Okay, just do a simple recursive formulation. So just 2 notes, right? The first note is that if I were to build this diagram just in the way that I've defined, right, I don't actually get this, right? I'll get something much bigger than this. Okay, so in order to get this, one thing you can do is you can apply a kind of bottom-up procedure to try to eliminate redundancies, right? So this gives you kind of the smallest or most compact network possible. Okay, and my second note is that this is closely related to state transition graph and dynamic programming, right? But we're not actually going to use dynamic programming to solve this problem, right? We're just looking at this graphical structure. We're going to use it to replace some parts of a broader problem. And then by replacing it this way, right, we're eventually still going to solve our overall 2-stage robust problem as a mixed integer program. Okay.
Jan, maybe I have a small question.
Yeah.
Just for
Yeah.
understanding, so when you have your flow formulation for such a diagram, so the flow, I know when you linearly optimize over the flows, the optimal flow is integer, but can it be that, I mean, the flow, there could be feasible flow which is fractional on each arc, so it's always guaranteed that the yi values here are 0, 1?
Good. So yeah, good. So if I were to think about using these diagrams to solve a deterministic problem, then you're exactly right, right? Naturally, the solution will be 0, 1. But in fact, as we'll soon see, if I were to put this in the kind of inner minimization problem, it almost always you'll get fractional flows, right? And it's essentially because the optimal solution will lie inside the convex hull, not necessarily at the corner point.
Okay, so you have to be careful when you have a nonlinear function over these diagrams, basically.
Yeah, I think so.
Okay,
Is there a question in the
yeah,
chat?
there's a question in the chat. Can this diagram be used for integer program other than only binary one?
You can, yeah. So there are recent works looking at extending this for general integer programs, yeah. But in this paper, we're only focused on binary programs. Yeah. Thanks for the question. Okay, great. Okay, so we're going to put it all together, right? We started with this problem, this very difficult min-max-min problem. Okay, we introduced this concept of selective adaptability, which allows us to generate this reformulation, right? And again, the complicating thing was this convex hull. Okay, and last but not least, what we can do is we can replace this y in this convex hull by introducing these z variables related to the flows on the arcs, right? And setting y and z together to satisfy the network flow constraints that I've shown earlier. Okay, so this is again, a static robust optimization problem. If I look at it, right, I have three sets of decision variables, X, which are binary, Y and Z, which are continuous, right? And then I have this inner maximization problem, which is also over a convex set. Okay, so for this, all you have to do is take the dual of the inside, right? And you'll get a single MIP formulation. Okay, so as you see, I purposely made the font small, right? The point is not to focus on this. The idea is just that we took this two-stage robust problem, okay, and we got a single MIP formulation out of it. Okay, so what's the problem here? Right, the problem is that there's no free lunch, right? So the one challenge is that these diagrams might be very, very large. Okay, if I want to formulate them exactly. So what do I mean, right? Well, what happens when these diagrams are really large, right? So if I have many nodes, this is the same as saying I have many of these flow balance constraints, right? AZ is equal to B. And then if these diagrams are very large, because there's a lot of arcs, right? It just means I have to introduce many of these continuous variables. Okay, so I've essentially replaced one problem with another, right? Now I have this huge mixed integer program. Okay, so what are we going to do, right? We're going to try to approximate, generate kind of more compact and smaller approximations of these diagrams. Okay, so the first kind of approximation is just to try to directly derive a smaller diagram, right? One smaller diagram, which I'll call d-approx. Okay, and with the smaller diagram, I'll just replace it here, right? So with the smaller diagram, I'll just replace it here, and my z's and my az is equal to b will be affected correspondingly. Okay, so how do I generate reasonable approximations of this diagram? Right, you can just imagine for this particular example, earlier when I had said, right, when you're building this diagram, you can merge states that are exactly the same. Okay, and there's nothing stopping you from merging states that are almost the same. Right, so I could merge these three nodes together. Okay, but once I merge these nodes, I have an important decision to make, right? Which is what state value do I assign it? Right, so remember, right, that this node had a state of 0, these two nodes had a state of 1. So I could assign this new node a state of 0 or 1. If I assign it a state of 0, right, if I always assign it kind of, in this particular problem, the lowest value of all the nodes that I'm merging, right, in this process, I'll actually get an outer approximation of the convex hull. Right, and the reason why I'll get an outer approximation is because, this is how much capacity I've used up. Right, so if at this node I've used up one amount of capacity, but when I merge, I say it hasn't used up any capacity yet. Right, this kind of allows potentially for infeasible solutions into this problem. Right, so this ends up giving me an outer approximation. And this outer approximation later you can use to generate a dual bound, right? Because the outer approximation means you have the feasible space is larger. Similarly, if I assign it a value of 1, right, this generates an inner approximation because I'm now cutting off solutions, right? So there might have been feasible solutions that come out of this node, but now I've cut them off by assigning it the largest value, state value in the nodes that I'm merging. Okay, and the important thing here is that we can control how aggressively we merge, right? So we can define these rules. And the general rule of thumb is that the more aggressively we merge, right, the smaller the network becomes, but the worse the approximation. Okay. We can think about a second kind of approximation, which we'll call multi-network flows. Okay. So this is especially important when you have multiple constraints defining this feasible region, capital Y. And so in all of the examples so far, I've just shown capital Y being defined by a single constraint, right? But you can easily have this case where you have some constraints here as well as your knapsack constraint, right? And so instead of trying to define, a whole one giant network for this feasible region, right, in which your state space, your states are kind of vectors, right? One thing you can do is still generate these smaller diagrams, right, for each particular constraint. Okay, and then you can pull them together this way, right? So my Y and I have Z variables that correspond to one specific diagram, Z variables that correspond to another specific diagram, right? And I can pull my problem this way. Pull the diagrams this way. Okay, so this gives us, again, in these problems, smaller formulations. And in this case, this would generate an outer approximation, right? The basic idea is if I have a capital Y that is equal to Y1 intersect Y2, right? The convex hull of this thing is less than or equal to if I took the convex hull of these two sets separately and intersected them, right? So if I define my network flow problem using this kind of structure, right? This will give me an outer approximation. What this means is that this model here, right, will generate both a feasible first stage solution and the optimal objective value of this problem will also give me a dual bound, right? Because the full feasible region is an outer approximation of the original. Okay, so this is essentially it for the technical content, right? So I'm going to talk a little bit about two sets of experiments and that'll be it. So again, let me just pause for 10 seconds to see if there are questions. Okay, so if not, we can look at some experiments. So the first experiment is a classic capital budgeting problem or a project investment problem. Right, so imagine you have n possible projects you can invest in, right? Investing in each project is a binary decision variable. Each project costs some amount to invest in, right? So G1 or G2 all the way to Gn, and you have a total budget, which I'll assume is H. And then when I'm investing in these projects, right, the uncertainty is in the project payoff, right? So this is kind of a classic capital budgeting problem. The question in the two-stage setting is which project to invest in the first stage and then the second stage if I assume that my payoffs in the second stage are discounted by some factor alpha. And so this just represents kind of a first mover advantage. Okay, so if you invest in something after uncertainty is revealed, you get much less of the payoff. Okay, so how do I write this problem, right? This is max, min, max. I'm trying to maximize the payoff, right? So in the first stage, I make, again, some investment decisions. Uncertainty is revealed to me in an adversarial way. And then in the second stage, I again want to make investment decisions. This G transpose Y is the budget constraint, right? Y are binary variables. Okay, and this is a constraint that says, if I invest in a project in the first stage, by definition, it has been invested in by the time I get to the second stage, right? And this is the objective that shows us that, if I only invest in something, in the second stage, then I get a payoff that's 1 minus alpha, right? So it's discounted by alpha. Okay, and if I look at the structure, right, this linking constraint between X and Y, it satisfies our selective adaptability condition. These are constraints that don't depend on X, right? So these are constraints that we can use decision diagrams to reformulate. Oh, well, a decision diagram to reformulate. Okay, so we ran these experiments for a capital budgeting problem from 10 to 40 projects. So we considered 3 versions of our network flow models. right? One is this exact version, meaning I exactly reformulate that knapsack constraint from the previous slide. One is where I merge nodes. While building this diagram, I merge nodes that are somewhat similar, right? So this generates a network flow model of medium size. And then finally, I merge more aggressively, right? So states that are not so similar. And this generates kind of the smallest, most compact network flow model. Okay, as benchmarks, we can consider K adaptability, where K is equal to 2, right? Which is, you can think about this as the smallest K adaptability model. And we also have solution times of the branch and price algorithm from the Aisha and Boris's paper. Okay, so this is an exact method. Okay, so these are the solution times from their paper. These are the solution times from K adaptability. Right, so the only thing to notice here is that as n increases, right, these problems really blow up in solution time, right? So this is kind of well known because these two-stage robust problems are really, really difficult to solve. If we look at our exact model, right, we see almost the same trend, right? The exact numbers don't really matter; they're roughly comparable, right? But the solution times really blow up. If I look at the solution times of this medium or smaller network flow problems, right, the solutions are much lower. Okay, so the natural question is obviously how good are these solutions, right? So let's look at the optimality gap of solutions of the models that are easy to solve, meaning they can be solved very quickly, right? So obviously when n is equal to 10 and n is equal to 20, right, the exact models can solve quickly, right? So this has an optimality gap of 0. Okay, but for these models here, that only took a few seconds for us to solve, right? The optimality gaps are also almost near optimal, right? The optimality gap is less than or equal to 0.4% on average. The other thing is, right, the way we design these models is that we generated them by considering outer approximations of the convex hull, right? So that by solving this model, it also simultaneously had generated a dual bound, right? And the average dual bounds for all of these problems were within 0.4% of the optimal objective value, right? Meaning that this can generate both a solution and verify that it's a very high quality solution. Okay. Any questions here before I move on? Okay, so in our second set of experiments, we study a problem that is a little bit more complicated, right? So we can think about assignment and resource allocation problems, right? So suppose there's some agents that you want to assign to some jobs, right? So the words agents and jobs are used very loosely. You can think about assigning anything on the left to anything on the right. Okay, each agent takes up some capacity A1. Each job has some total capacity B1. And the goal is to maximize the quality of my assignments, assuming that the arc quality, the match quality is unknown in the first stage. Okay, so the problem we're going to look at is in the first stage, I'm going to select some percentage of arcs, right? So for example, 30% of the arcs. In the second stage, I'm going to generate assignment solutions using only the selected arcs. Okay, so these problems come up, for example, if you want to train agents for specific types of jobs, you want to inspect the match quality of certain arcs before making a final decision, you want to identify important arcs in this bipartite graph, and so on. And the mathematical formulation for this problem looks like this, right? So again, max, min, max, right? The innermost problem is this assignment problem, right? So these are all constraints that don't depend on X, right? So this is capital one. So I have constraints that are related to the capacities of each job, right? So what does this say? This says, you know, if I add up all the A's for the agents that are assigned to a job M, right? They cannot exceed the capacity Bm. Okay, and the second set of constraints just say that each agent can be assigned to at most one of these jobs. And what we're going to do here is we're going to generate not a single decision diagram for this capital Y, right, which would be huge because you would have to have state vectors capturing all of these constraints. But I'm going to generate a decision diagram for each of these capacity constraints, right? So each of these capacity constraints that look, again, very similar to knapsack constraints. And then I'm going to solve this as a multi-network flow MIP, right? So all this means is that, we looked at our static robust problem and I'll have something like this, but with more than 2 diagrams, right? With n number of these diagrams. Okay, so we tested our problems on our algorithms on a variety of problem sizes. Different number of agents assigned to different number of jobs, right? So you have 20 agents to 2 jobs, up to 25 agents to 8 jobs, right? A total of 250 instances. These are the solution times for our what we call these multi-network flow models, right? So they're quite fast until we get to much bigger instances. And just as reference, right, this is a K adaptability model where K is equal to 3, right? And these are the solution times. Okay, so this is a figure of our results. On the x-axis, we have the optimality gap. And I want to emphasize here that this optimality gap is based on the dual bound, right? So our model is able to generate a dual bound, but as an example, K adaptability would purely generate a primal heuristic, right? A primal bound, right? So you wouldn't get a dual bound. So this is based on the dual bound that we're generating. And on the y-axis, you have the number of instances that are solved within some level of optimality. Right, so if I look at this first column here, what this says is that 86 out of 250 instances that we tested, right, generated an optimal solution and verified its optimality because the dual bound was equal to the optimal objective value, true optimal objective value. Right, 223 out of 250 instances had an optimality gap of less than 1%, and by 3%, all the instances generated solutions that were within 3% of optimality. Okay, so that's basically it, right? In conclusion, 2-stage robust binary problems are very difficult to solve. In this talk and in our paper, right, we propose these constrained network flow models, right, which you can reformulate as mixed integer programs, right, which we show are versatile because you can control the size and the approximation quality. They're fast to solve and easy to implement in standard solvers, and we showed that they're very effective in generating good solutions and bounds. Okay, so if you're interested in learning more, you can check out our paper here on arXiv, and I should be uploading a more recent version soon as well. Okay, thank you.